All right, welcome to ECS CDM12, Media Computation. Today we'll be talking about math, angles, and randomness. So here is, I think, a really interesting example. You'll find a lot of tutorials on this. These are flow fields, and they're going to rely on a lot of the concepts that we work today. They're also fairly advanced. You'll need some larger structured data types like arrays, which we haven't talked about yet. But here is where this sort of work is
Flow fields are a classic generative art technique that can be used in many different ways and can produce all kinds of beautiful results. And yet the way they work under the surface is surprisingly simple. In essence, a flow field is just a rule that tells a particle how to move around a space based on its current position. The most common way to use a flow field is to create a large group of particles and simultaneously move each of them in the direction that the flow field indicates, drawing a line behind each of them as they move. So, to start, we'll randomly pick a bunch of points on the screen and create particles at those points. As a trivial example, we can create a flow field that just moves all the particles in a fixed direction. More interesting flow fields will make the way a particle moves depend on the current position of the particle, so that not all particles will move in the same direction. For example, we could define a flow field that moves all the particles towards the center of the screen.
Okay, that soundtrack is actually part of this video.
Of course, there's no reason why we had to pick the center of the screen. We could just as easily pick any point on the screen to have the particles move towards. Rather than having the particles be attracted to just one point, we could instead pick multiple different attraction points that each attract all of the particles, and make it so particles are more strongly attracted to the attractor points that are closest to them. If we pick these three attractor points, then the flow field will behave like this. We could also choose a much larger number of attractor points. Having a set of attractor points isn't the only way to make a flow field. All that you need to create a flow field is just some way of assigning a direction to each point in space. One common way to do this is to use Perlin noise, an algorithm for producing random values with smooth gradients. Perlin noise looks something like this. To turn this into a flow field, we can just map the value of the noise at each point in space to a direction. We can map the lowest values, which are represented here with the lightest color, to an angle pointing straight upwards, and rotate the angle clockwise as the value increases, or in other words, as the color gets darker. Using this noise to define a flow field, we'd get something like this. Here's one of my favorite ways of defining a flow field. Like the example I gave before, this kind of flow field...
All right, that explains the basic concept, and you'll learn a lot more today about how this works. Angles, flow fields, we're even going to be talking about Perlin noise today. And the slides are up, and the examples that we're going to talk about today are in the class materials folder, Google Drive folder, under the Math, Angles, and Random subfolder. We'll have a set of projects to work through.
We're attracted toward
Per our pattern. All right, so we've talked about this. So let's cover some of the basics that you've read about in the text. Basic math. So we didn't spend a lot of time covering this explicitly. I'm assuming by this point in your academic careers, this should be well within your knowledge sphere. If not, happy to help. But basic math, arithmetic, addition, subtraction, division, multiplication, and in the case of programming, assignment. Once again, equals that you've used in your algebra classes is not the same as the equals we use here, which is assignment, as opposed to making equality on two sides of two statements on two sides of an equal sign, as in algebra. And it's not the same as checking to see if the left is the same as the right with our double equal sign Boolean operator that we've used recently. Here's an example of arithmetic. We're defining a variable, float A, and we want to assign it a value. Well, this value takes some arithmetic to figure out, right? 6 plus 5 times 4 divided by 2 minus 1. Now, when you put a statement like this in, processing does all the arithmetic for you and provides A with the result. So you want to follow the standard order of operations, which sometimes can be a little confusing. Luckily, when we're dealing with basic math in computational metaphors, it doesn't have the same ambiguity points. I mean, you've probably been like Facebook or Instagram and like your aunt or uncle probably post like, what's the answer to this math problem? And people completely disagree because there's a different way of checking out PDMOS, or the order of operations, which people that learned before a certain time learned a slightly different order, a slightly different algorithm than folks that are learning now. So it makes some math equations come out differently. But in this case, the result is 15. Now, we have this idea of floating point values versus integers. Who can tell me the difference between a floating point value and an integer? A little bit of bringing back past lessons. Floating point, yes.
Is it that floating point values are decimals and then integers are just real numbers?
Exactly, right? So floating point values can have a fractional value. Right? They get them a point. The numbers behind it, a decimal that we often call. Now, I don't want to say that you can only have whole numbers with integers, because whole numbers denotes 0 and above. Integers can be negative as well, right? So the set of things that are integers is defined as integers in math, right? So whole numbers that have no decimal place, have no fractional bit, but are negative or positive. So when we're dealing with math in processing, you can have integer math. So in this case, when you're doing math with integers, the result is an integer. So basically what happens is lop off anything that's a fractional value. So 3 divided by 4 would be 0.75. Well, that 0.75 gets chopped off and is 0. You're basically rounding down. Or I guess in negatives. Yeah, rounding down as well. Now, rounding up in negatives. When you chop off the fractional bit, you're rounding up. So with integers, if they're involved with math operations, it gets a little complicated. See, here we have mixed integers and mixed floating point values, right? So there's some tricks here. So it only holds true if you're doing integer math. The above would be 0.75 and 0.6 respectively if you're doing floating point math, right? But with integers, it's different. No decimals, chop them off. There's some rules for this. So this can be a little surprising. So let's cover this. So processing will decide if a number is an integer or float based on whether it has a decimal place, right? So if you simply put a 4, it will count as an integer. If you put a 4.0, it will be interpreted as a float. That's why you often see point zeros in code. That way you disambiguate between the two types of numbers that we deal with. Now, when there is all integers in your arithmetic, it gets interpreted as an integer, right? So as you go, as you perform each operation, each division, each addition, each subtraction, each multiplication, that decimal value gets lopped off. Now, if there is a floating point value mixed in with integers, then it's typically interpreted as a floating point value. So in the first case here, 3 divided by 4, both without decimal places, would be integer division. The result would be 0. Now in the other case, 3.0 divided by 4, because there's a 0.0 there, this will be interpreted as a floating point value, and the result will be 0.75. And you can check this on your own. You can put this into print line statements. You can write math on your own, print it out, see what the values are. If you're ever confused, it's an important thing to do. You can easily get tripped up on this and think you're dealing with decimal values when you're actually not, when it's being truncated or the decimal part's being chopped off for you. Another thing to be aware of are the short forms. We touched on this briefly last class. Well, there's some ways to more compactly represent some math for you, some arithmetic. So like the increment operator, a++, it's the same as a equals a plus 1. just shorthand for that same thing. The decrement operator, a minus minus, is equal to a minus 1, or a equals a minus 1. Likewise, plus equals. You can add 5 to a number by doing a plus equals 5 instead of a equals a plus 5. Same with multiplication. And there's also short forms for division and subtracting a value. Any questions on these? You'll see this a bit. This is a good one to keep a reference for. Now, also one we talked about previously is the modulo operator, which simply gives us the remainder. So here we have a percent, which is the modulo operator. We call that mod. B equals C. A mod B equals C. So in this case, we divide A by B, and C is the remainder. And it's interesting, right? Because C is always less than B by default. Because if, it's the basics of division, right? So you can never be, the remainder can never be equal to the divisor. A mod B. So here are some examples. 14 mod 3 is 2. Right? So 3 times 4 is 12. There would be 2 left over. 2 is the remainder. 4 mod 7 is 4. Hope this is fairly straightforward, but it's important when you see percent signs. This is not one you normally come across in your math classes. So I just want to make sure we have this in our minds. Percent operator, asterisk or star is multiplication, / is division. Well, those map pretty well. One you'll also see in programming, we won't use it a whole lot here, is the caret or shift 6. That's usually used for exponentiation. Angles. Trigonometric functions. I'm sure, hopefully most of you have been introduced to trigonometry at this point. You may have various degrees of enmity with trigonometry. We're going to use it fairly simply in this class. We're not going to have you do any, advanced trig proofs or anything. If you want to do some advanced trigonometry in your assignments, feel free. But we're basically going to use cosine and sine for this class. So, in nearly every programming environment, the trigonometric functions use radians and not degrees. So we talked about this before. This is a mathematical definition using pi, where 2 pi is 360 degrees, pi is 180, and 0 is 0 degrees. Radian function maps degrees to radians. It's very handy for us. We've been using that a lot already. There are some constants defined for you. So variables that you can't assign to. There's the sealed boxes you can't change the value of. You can look inside the box and get a value, but you can't alter it. There are 2 of these constants provided for you, pi and 2 pi. So if you want to have it 360 degrees or 180 degrees, you can use these values here without using the radians call. Right? So if theta is in radians, you can use sine theta. If theta is in degrees, use sine radians theta. Questions? We're starting off pretty dry. We'll get into some examples soon. We're moving on through. Okay, let's take a look at the cosine theta example. All right, so we're using the goldfish color scheme. We're doing some basic setup with the window size, stroke size, setting the background to clear pond water, setting the stroke to giant goldfish. And we have H scale, V scale, 0 line. Really what's going on here is we're using the cosine of previous Z plus a 0 line. We're going to draw some interesting things. Let's just take a look at this, and then we'll take a look at the code. Right? Here what we're doing is drawing some waves. Going to my windows here. All right, so here what we're doing is we're setting the height, the vertical and horizontal scales of our waves, right? So we can show how tall and long they are to actually put those values into pixel values, because when you deal with sine and cosine, you're getting values you're getting return values of 0 or -1 through 1, right? And that's not super handy if we use those directly, right? Because that'll be -1 to 1 pixel, right? That won't look like a wave. That'll look like maybe an anti-aliased line or something, or a line with a lot of aliasing artifacts. Now we scale that up. We make it 200 above 0, 200 below 0 for a height of 400. We keep track of where we were previously, and so we're incrementally drawing points or small lines together to make these curves. So we're going to do this for an entire 360 degrees, and we're going to draw each degree and map. We're going to unroll this circle into a wave, which is what sine and cosine are great for. So we're basically making sure that we respect our horizontal scale and our vertical scale, and we're doing cosines of radians of I. So basically we're going through each degree, mapping it to radians, and getting the cosine of it. And we're adding the 0 line here to make sure that things are in the middle of the screen. We have our 0 point here. And so we're drawing a line for each degree. So little line. You can tell here cosine and sine start offset from each other. So that first line, since they all start drawing at the 0 line, the first line is actually stretching down to the bottom to get to the starting point, the 0 value. And we're drawing, for each degree, 360 times, a small chunk of these lines. One little unit. So this is actually, if you looked at this in a 3D editing software or something, you'd see a bunch of really tiny lines. The surface isn't actually curved. If you looked at it really close and zoomed in, it would be a bunch of jagged edges. But we are making enough jagged edges in a close enough proximity so it looks to us as humans at this scale as a curve. This is how 3D graphics are in computers. I mean, how many of you have seen a polygon landscape? Seen a wireframe outline of a 3D world? Right? Certainly most of you have. Those outlines are how computers actually structure video output. Everything you're actually seeing, from the most nuanced video game to, what's a good recent CG artifact? Anything by Pixar? Those are actually a bunch of very small flat surfaces and lines that are have various processing techniques and have a high enough density that they look very much like hair or teeth or eyes or faces or fuzz. So we're using that effect here. Our first line here is cosine. And then we're drawing sine. Any questions about this? Notice I'm skipping over some details. We're not going pedantically through this because at this point you should have built enough base to understand a good chunk of this code. If not, please come to office hours. We'll have some simpler examples here, but this is just showing off how to use trigonometry in some effective way. All right. Pseudo-random numbers. This John von Neumann quote. Anyone who considers arithmetical methods of producing random digits is, of course, in a state of sin. Any idea why this quote is meaningful? What's random? What's a good operational definition of random? Yeah? Unpredictable, exactly. Chaos. Well, how do we get that from a machine that works in zeros and ones in a very deliberate way, a very discrete way? It's like the antithesis of random, right? We actually want the structure. Random is bad for computers, but we use them anyway. What's the dissonance here? No brave souls? Yes.
It's using the same algorithm over and over again to yield results, so it doesn't really seem unpredictable.
Yeah, so that's how computers operate. And randomness in computers operates in the same way. It's actually quite predictable random. That's why we call it pseudo-random. If you use random, it will look like you're getting random values in the traditional sense. But there's some complex math and equations to make it have the illusion of random. And we want bounded random, right? We want a random value between 0 and 255, between 0 and 1. That's if you wanted a random number of all numbers that could possibly exist, it wouldn't be within those bounds. So now we have to somehow have algorithms that look random when you use them operationally in your code, procedurally in your code, but also have some guarantees that we need to actually have it run in a computational environment, in our world of zeros and ones. That's very deterministic. That's why we call these pseudo-random. They're random-like, but not truly random. Now, you can actually get random numbers in your computer and not pseudo-random, which is very interesting because what you do is you make a call to NIST, the people that define time and, for the United States. And they actually look at atomic decay clocks, and they'll randomly sample a value of some subatomic particle that we know has much more true random properties. And then they simply sense that value and return it over the internet to you. Right? So they're looking at a true random source and then sending that to you. So it's actually outside of the computer. They're actually sensing something in the world. They're going outside of the digital to pull a random value because that's sort of necessary for very true, strong forms of random. I thought that was pretty cool. Anyway. So how do we use this? Well, for us, we can get a random floating point value by using the random function. Now, the random function returns a pseudo-random number from a uniform distribution, from 0 to max. Let me pull up the documentation. Browser, Chrome, random. There we go. So this is documentation for random. Encourage you to look this over. Now you can see random generates random numbers. Each time the random function is called, it returns an unexpected value within a specified range. If only one parameter is passed to the function, it will return a floating point number between 0 and the value you give to it. So if you want a value between 0 and 1, you call random with the parameter being 1. If you call it with two values, for example, -5 and 10.2, it'll return values in that range, -5 up to, but not including 10.2. And here's some use cases for it. Floating point values. And if you want an integer out of this, and you don't want a floating point value, you can simply just force it to be an integer by wrapping a random call inside the int function, which will take a floating point value, chop off the end, and give you an integer. Convert it to that for you. So let's take a look at raindrops. All right, so we have a raindrops example here. Setting up the window, 600 by 600, white background, frame rate of 20. Setting a stroke color to a light and slightly transparent gray. In the draw function, the first thing we're doing is we're picking a number between 0 and 1, but not including 1. between 0 and up to almost exactly 1, but not quite. Now, because we have this number between 0 and 1, you can treat that like a percentage, right? So it's like rolling the dice. For those of you who play D&D, it's like the 100-sided dice. So rolling 2 d10s, where one of the d10s is interpreted as the tens digit and one is interpreted as the singles. Now, if we picked between 0 and 0.5, we're using this fill color. So if it values between 0 and 0.5, 0 and slightly less than 0.5, the fill will be this color. If now we're picking, if pick is below 0.7, so that would be 0.5 all the way up to and not quite including 0.7, the fill will be this color. And otherwise, in this case, if it is 0.7 or above, the fill will be this color. And what we're doing with that is we're drawing an ellipse with that color, with that fill. So now what we're doing is we're getting a random offset with a random value of 40. And basically we're drawing around that offset value with a random height and a random width. Any idea what this will look like? You have an intuition? Yeah, so the ellipses will be a random width and height. They'll be randomly offset. And they'll be randomly colored. Within, well, we'll choose a distribution of colors from this range. Purple and pink rain. One more time. Right, so what we're doing here is width and height are the screen width and height. So we're placing them randomly throughout the screen. And we're placing them, we're giving them a width and height. And the width and height is 44. So 44 pixels will be the smallest raindrop. And then they'll go up to plus from 0 to 39 more. So there'll be width of 44 all the way up to 83. We can change this. Let's say we want way less of this first color. So by picking this distribution, we change the amount of purple to be way less. So 1 out of every 10 on average of these raindrops will be purple now. Whereas for the last example, half of them were. Right? So that's a great way to use random. Use it for dice rolls. Use it for probability. Get out of here. That was turn on the webcam. I don't want that. Right, so this is a raindrops example. Using random. Does random make a little more sense now? Excellent. Now we have noise. So here is where we're getting into something a little more interesting. So noise takes a time value. So here, noise is an implementation of Perlin noise that returns a number that must be somewhat close to the number for the previous time. So what's interesting here is it's not just simply random where you get things all over the place. Random in this case, noise in this case, gives you values that are close to each other that you can't predict. So it has a gradient. If you map these out, it would look smooth. Let's see, I didn't prep this, but let's see if this will work. I'm going to go back to raindrops and see if we can use noise instead of random for their placement. Okay, so what we need to do this? We'll need a time value. So what I'm going to do is make a int frame count. Start off as 0. At the end, we'll do frame count plus plus. And instead of offset being random, we're going to use noise of frame count. Right. Let's see if this works. Okay, maybe it didn't. Oh. All right, so it's not random with noise of frame count times width. And then we're actually going to call this position offset, and we're going to use that here instead. This may look a little weird because this should travel in a line. Oops, ellipse. Oh, I did all position. Oh, there we go. Need them all. Right, so now things are appearing closer to each other. It's a little more of a gradient. And 1 is a little high, it seems. So not appearing right next to each other, so 1 is too big of a value. So our little experiment wasn't completely successful, but let's continue on. Get rid of all this. Fine, just go away. Let me confirm I didn't break it, because I am saving on the Google Drive. There we go. Back to the presentation. Right, so the number you get back from noise is from 0 to 1. And you can use this in 1 dimensions, 2 dimensions, or 3 dimensions. This noise can have volume. And you can control the level of detail in the noise. So there's some interesting properties of Perlin noise, not the fact that it's just gradients, but the fact when you multiply it by factors of 10, it works like octaves in music. So, a middle C and a high C, when played together, they'll reinforce each other, right? They're the same note, but played at 1 octave above. So they harmonize. Well, there's also that same level of harmony in Perlin noise. So as you add octaves, what happens is you get additional levels of detail on top of your already smooth gradient surface. So you can add 1 octave and get like a bump like this. If you add another octave, you'll start seeing little details on the surface. You add another octave, you'll see even more little details on top of those original little details, but everything will still be smooth and in a gradient. So Perlin noise won an Academy Award. This algorithm for generating noise with particular properties is an Academy Award winning algorithm. It's very useful for her. If you've ever seen like mist and clouds, typically in movies or in CG, those are typically using Perlin noise. Flames also tend to use Perlin noise. It's a very prolifically used source of random. And here's sort of what it looks like. So here, Perlin noise, you get something that's continuous, right? You get something where the line does not super disjoint. But if you do something like true random, and you probably have seen this because this is in the reading for today. It's sure you all read the reading ahead of time. As noted in the syllabus, you'll see the difference between how Perlin noise and random look. Right? One, you can interpret in very human ways, right? This could be a graph. like it is. This could be mountains. It could be a landscape. It could be the border between water and land. Whereas it's much harder to interpret something that bounces around a lot in these more human, meaningful ways. There's random. Is closer just to getting random values. Perlin noise has gradient constraints and octaves. All right, so noise always returns a value between 0 and 1. The smaller amount of time that you give it, so if you give it like 0.1, if you give it like 0.1 and 0.2, you'll get something that looks more smooth on a gradient than if you give it like 10 and 100. You call noise 10, then you call noise 100. The difference between those two could be pretty great. If you call it smaller value, like noise 0.1 and then noise 0.2, they'll be much closer to each other. There'll be much less space between them in the 0 and 1 range. So you must increment time to a different value, right? If you keep calling it the same time value, you're going to keep getting the same result out of it. Small increments will cause the noise to change slowly. Large increments will cause it to change in more significant ways. Right, so I kind of jumped the gun on the raindrops example. I wanted to show that earlier. But this is sort of the framework that we use for probability distributions. Right, if you want something to happen like 20% of the time, roll a number between 0 and 1 with random and see if that number is less than 0.2. Here's one you can try on your own. Ellipse with random width, random height, which is how the raindrops work. With that pretty well. All right, so now we get even more interesting effects here with seeds. I'm curious, does anyone already know what random seeds are? Seed values for random? Okay, there's one person. Excellent, excellent. This is really, I think, pretty interesting. Unlike true random, you can provide seed values to our pseudorandom, noise, and random functions. Now, what does that do? Well, that means if you have, if you set it as a seed, let's say 32. If you give noise seed the value of 32, and you call random 0 to 1 a bunch of times, and you restart your program, you'll note that those random calls, you'll get the same sequence of numbers every time. If you call noise seed once, make a bunch for 32, call a bunch of random numbers, but then you chain and you see those numbers, then you call it again, but with now noise seed set to 33, you get a whole different sequence of numbers. If you set it back to 32, you'll get that first sequence again. So what noise gives you is you still have like a hard to predict sequence of numbers, but you can recreate your art. Let's say you have art that, or raindrops, right? You give it a seed. You will always recreate the same raindrop pattern every time. If you get a different seed, it'll be a different pattern. This is very useful in generative art where you want to create a bunch of images and samples. And you're like, okay, well, I generated a bunch of these, but I really like that one. How do I recreate that? What sequence made that cool thing happen? Well, usually when you do this generative art, you save the seed values with it. So now you can completely recreate that art that relied on random with the seed value. How many of you played Minecraft? How many of you have used the seed value in Minecraft? This is the exact same thing. This is the heart of how Minecraft random generation works. This is seed, world seed. All right, let's take a look at the Perlin noise example. So we'll delve into this a little bit. Get rid of raindrops, back to Perlin noise. Okay, let's actually show it to you. Here we go. All right, so here is our Perlin noise example. This is directly from the book with my addition of processing output window. We have time and we have time increment. So note, this is the increment that we are using for our Perlin noise. we're using a 0.01 increment in time. So we're expecting a pretty smooth gradient. It's a fairly small number. Background. I changed the colors a bit. So what we're doing here is we're calling noise, we're getting a value from noise called in. So that would be a value between 0 and 1. We're calling noise, we're calling noise times time, which is a value of 0 and 1, and we're multiplying it by width, right? So what we're doing is we're changing the width of something in a smooth way instead of a poppy way that completely ignores the previous values. We're incrementing time by 0.01. So next time we use it, it'll be slightly bigger than the time before. We're setting the fill color to black, and we're drawing an ellipse with our width and height, the width and height in the middle of the screen, with the size of n by n. So it'll be a circle in the middle, of radius n. Once again, we're getting n from noise over time times width. So it could be as big as the screen, or it could be almost like 1 pixel infinitely, very small. It could be 0. What do you think is going to happen? The reason why I keep asking you what do you think is going to happen is because this is a critical part of interacting with your processing, iterative design, writing something, thinking about what will happen, understanding why it did, and then revising, writing and revising. Did you expect this? I was almost pretty mean into the black background with like a red eye, but with a texture of HAL 9000. The computer's staring at you, but it's all just noise. So note, this is Berlin noise, right? So it's growing and expanding. The values that you get from small time increments are close to the values from the previous time increment. Now, I just want to drive this home a bit. This could be a little poppy. We'll change this instead of noise. We'll set it to 1 and do random. Right? That, which I won't show you for too long, is definitely a different quality than this. Right? So now you see why noise is interesting and different than just random. Yes?
Can we change the speed of it?
Yeah. So there are 2 ways to do it. You can either make the increment more fine. We can make the increment much slower. Okay, maybe that was too slow. You can see it's just barely shrinking. Okay. Let's do 5 times. So half the original speed. So you can change the time increment, which means you're going more in a fine-tuned way over that gradient of noise, over the Berlin noise. Or, go back to original value, you can change the frame rate. Higher frame rate will make it move faster. A lower frame rate will make it move slower. Two ways to do it. Yes?
Can you show an example of kind of some of the width?
I'm sorry, what?
Can you, or maybe just explain to me, limiting the width, right? The width right here is just according to the time boundaries that you set. How would you do that? Just limiting how much it could expand.
You mean this?
Yes.
Yeah, I mean, so this is width is the width of the screen, right? That's a predefined variable given to you. Right, and so you could replace that with whatever you want. 300. So now the maximum size of it will be 300. Right, it's a lot smaller now. Because the screen was 700 by 700. And that was the max size it could be before. Now we set it at 300, so it's going to be much smaller. But still with the same gradient values. You're welcome. Let's change this back. Here we go. Listen to me groan dealing with this laptop. Okay. Half hour left. We can do this. We can do this. All right, so that was Berlin noise, right? And so here's the basic example. I changed the colors and some parameters slightly from what you see in the slides. So this is sort of the vanilla version. Now, this is something that's handy for a lot of projects. Polar coordinates. How many of you have worked in the standard two-dimensional XY plane Cartesian grid before? Drawing graphs, slopes, lines, intercepts, trig functions, right? That's one way of viewing the world, right? The center origin is at 0, 0, where the x and y meet, and then you have your top quadrant, your 4 quadrants. You can place points on that by giving an x and a y value. Now, polar coordinates are different. The origin is still in the center, but let's say you want to draw a circle. Well, how would you do that with x and y values? Or you'd have to use sine x and sine y plus a width, and you'd have to, for every point that you wanted in the circle, you'd have to calculate where that is and draw it. With the computer, that's tough. You do some for loops and all that, kind of like where we do the sine waves. So that's a lot of points. It's a lot of drawing. It's a lot of calculation. Now, it's pretty easy when you have paper, right? You get the compass out, you put the little pokey bit in the middle, and then you adjust that little pencil in the little bracket, and you get it out just right, and you make sure it's sharpened, and then you spin the thing around, right? And it draws a pretty good circle. Well, that's seeing the world still as a grid, right? We're still like calculating all the 0 and 1 values to go around the circle. It's a lot. It's like this. Now, polar coordinates are different, right? The 0, 0 is still there, but basically you're dealing with a different coordinate system. You're not using x, y values. You're using a radius, or how far away you are from the center, and a theta value, which is what angle you're going out from the center from. Right, and this is really handy for drawing certain types of procedural art. Like if you've ever seen those cardioids that go and loop around, or if you've perhaps looked at some spirograph type of things. All of those are dealing with offsets and angles from the center. This is a very handy mode for making certain types of digital art. Polar coordinates are more convenient in these cases when describing a circle. When you want to specify an angle from the origin. Remember using that arc command when you drew Pac-Man? And why that was a little confusing to figure out exactly how to get the mouth in the right place? Well, that's implicitly using the angles that you gave it for the last parameters. We're explicitly using polar coordinates. When you want to specify a distance from the origin, a radius, a center, arcs, all these are very handy. When you're dealing with this circular space where things should be predominantly circular in their character and quality, and your origin-centered polar coordinates are your friend. And you can convert polar coordinates to Cartesian coordinates with this. If you have your polar coordinate, so your r, and your angle, theta, you can get the x value simply by multiplying r times the cosine of your theta value, and you get the y value by r times the sine of your theta value. Basic trigonometry. Easy to convert between the two. So you can use polar coordinates in your own program just by doing this. You don't have to set any special drawing mode in processing to draw polar coordinates. You can simply just use this formula and pass around r's and thetas. All right, path drawing example. Let's see, do I want to do this right now? One moment, please. No, I don't. I'm gonna skip that example for now because I'm gonna show it off later. I think it fits better later. All right, this is a graph of noise. Right? So now if we're generating values of noise between 0 and 1 and dividing into 0.01 buckets, so this is a histogram of the Perlin noise return values, you'll notice that there's a big clump right in the middle. Right? For those of you who have taken some more advanced math, this looks like a Gaussian distribution, right? Where it looks kind of like a bell curve, right? There's a lot of clustered points around 0.5, but less around 0 and 1. So the height is the number of times that, so we ran noise a whole bunch of times, a whole bunch of different values. And this is the result. So the height of it is how many times that value in that bucket of size 0.01 has occurred. Way more in the middle, way less on the edges. So it's biased around the middle, 0.5. Let's take a look at the noise distribution. Uh-oh. Let's take a look at some new batteries. Oh yeah, dead battery. Pardon me, one moment. Any questions about this that I can think about while I'm changing batteries? Okay, I hope these are these. Oh no, someone put dead batteries back in the package. How rude.
That's so rude.
That's really rude.
That is messed up.
Okay. Hopefully they didn't do that in this one too. Look at this. Someone did that and cost us all this class time. Okay. All right. Better? Better. Thank you. Sorry for that interruption. Let's take a look at the noise example. Our noise distribution example. All right, this code will plot the distribution of values returned by calls to noise. You can see that all the values are not equally likely, i.e., it is not a uniform distribution. Instead, the distribution is based towards the middle, like we just talked about. Note, this code uses arrays, which we haven't covered yet. So I don't expect you to understand all of this code. Particularly line 11 is where we define an array called buckets. We'll get to this. I'll leave it a bit of a mystery now. I'm sure some of you will be able to figure it out or have read ahead. We have 100 buckets. This is our time increment for noise, 0.01 again. And we have a 1000 by 1000 screen. Make a new array, set the frame rate to 100, set the noise seed to 100, background set to white, and we're going through j is less than 20. So we're sampling through the noise 20 times. We're going through and generating one value. We're generating a number of buckets values, and we're placing them in the correct bucket. We're generating noise, putting in the bucket. I guess we're generating 20 samples per frame. Okay, that's what's going on. 20 samples per frame, per time of draw, and we're then finding which bucket those samples belong into. Right? So if the value is 0.2, we want to put it in the bucket that holds the value from 0.2 to 0.21. Since we're doing 100 buckets, or our bucket size in this case is num buckets, which is 100, yeah. So every 0.1 value change we get, so we put in a new bucket. And then we're going to draw each bucket 10 pixels wide. Oh no, oh no. You know what I forgot to add? window title processing output window. For those of you who are curious, this is the window title that I'm using for OBS to pick up the particular screen to show. And now it finds it. So we're sampling noise 20 times every frame. And we're adding simply a value to that bucket. So every time you see it grow by a small increment, by 10, that means noise generated a value for that particular bucket. So we're building this distribution on the fly. So that's how we solved it. That's how we made the graphs here. Just let it run for a while. Now, if we use random instead of noise, what do you think is going to happen? We talked about a uniform distribution. Let's see what one looks like. Maybe. Yep, there we are. So how's this different? Other than being like creeping doom, the Demon King is invading the land here. Right, all the buckets are about the same height. There's a little variation, but on average, it's the same. At a broad scale, it's uniform. Right. So another view between the difference of random and noise. Now, we're at the end here. We're at our last slide. We have 2 examples to look through. So trig functions are very handy because they can provide us a nice way to give a natural appearance of variation, like a wave. So we talked about polar coordinates and sine and cosine being how you draw a circle. Basically what we're doing is we're drawing, the x or y values, in this case the y values, as it varies, as you would go across the circle, and we're just unrolling that. Like you've probably done a bunch of times and drawn in trig, so that you do in your trig classes. So this is how that looks, right? When pi starts going negative, you go to the left, sort of wave, and with sine, and when you go positive, wave in the other direction. So sine starts at 0, wave would start at 1, or cosine would start at 1, so they're offset from each other by 90 degrees. Let's take a look at pendulum. Get rid of noise. Pendulum. All right. So once again, we have time, a small time increment, base values of x and y, a base radius of 250. We have this g stopped variable. We have our goldfish colors again. Output window, frame rate 60, size 600, 600, background set to Unreal Food Pills. Draw. So if not g stopped, so this g is just, are we simulating or are we not? Are we moving the animation or are we not? Just like down here. So if you press S, G stop is true, press S again, G stop is false. It toggles between true and false every time you press S, which simply gates us doing anything in draw. So it's our control. Are we drawing or not? Our background set to AOE. Theta, we're setting to be 60 times sine of time plus 90. So we're using sine of time here. So we're getting an oscillation over time. So as time increases, we're going through the sine wave. Incrementing time, getting our some x and y points. And so what we're doing here is we're getting these x and y points from a base x and a base y times, using polar coordinates, r times cosine theta to get the x point, and r times sine of radians of theta to get the y point. Right? So we have the center, we have a radius, we have x changing with the sine of cosine of theta, which changes with time. And we're doing some drawing. We're setting the fill giant goldfish, setting the stroke giant goldfish, drawing a line from base to a point, and then we're drawing an ellipse at a point with size 40/40. Based off the name of this code example, what do you think is going to happen? Get a little Edgar Allan Poe. Maybe I should have made it a scythe. Sickle. The room. We have a pendulum. And we're controlling the position of the pendulum with polar coordinates, which is a much handier representation than trying to natively work with the x and y values. So here's an example for you using polar coordinates in interesting ways. Like the opening scene of Chrono Trigger with the clock. I recommend playing that game. Super fun. All right. Any questions about pendulum? All right. Let's take a look at our last example. Kintsugi. Does anyone know what this term means? I'm doing a lot of Japanese references lately because I'm going to Japan in November. So this is the art of repairing broken things with gold. All right. So with that said, we have some floating point values, x and y. We have the size of a step that's we use with noise. We have a time and an increment. We have a G stopped again. We have a color of slate and a color of gold. 100 by 1000 by 1000 window. Background is set to slate. We're setting a noise seed of 10, a random seed of 100. X and Y. X is set to width, so all the way to the right. Y is set height by 2, so in the middle height-wise. Stroke is set to 5. Stroke is set to gold. Stroke weight is 5. Stroke is gold. So while we're not G-stopped, same G-stop as before, stops and starts simulation. I guess I should have shown that. So when you hit S, it'll start drawing and stop drawing. Toggle when you press S. We're getting previous X and previous Y. So, just like before, like we drew with our sine waves, we're doing small little chunks of lines adding together to make a larger thing. So we're getting theta being 360 times the noise of time. So basically we're interpreting the 0 to 1 value from time as a 0 to 360 degree value. Doing some temporary variable calculations. So we're using polar coordinates yet again. So as our theta changes with noise over time to values of 0 to 360, we're interpreting that 0 to 360 degree value in radians, setting it to cosine, and multiplying that by r. So what is this getting us? Well, this is the same thing with the sine of radians of theta times r. This is getting us a new value. So we're like, if you look at the current value where we're at, we're setting a theta value to be a noise value between 0 and 360. Let's say, 30. And then we're taking that times our r value, which is 4. So 4 pixels. So we're drawing a line in some direction described by noise in theta and time. And we're moving in that direction by 4 pixels. So every time we draw a line, we're looking at the center of a polar coordinate system as the center, or as the draw location. And we're printing out the values just so you can see them go. And we're doing something else. Since we're moving in a line, we're bouncing around the world. If we go off one side of the screen, or the top left, bottom, or right, we're putting it right back to our initial values. We're going right back to our top left side, our x and y, our temp x, temp y values. I'm sorry. If we have not hit a side, we're updating our values with our new polar coordinate values, our movement by 4 pixels. Sorry, I misspoke there. Otherwise, we're setting a new value to start from again. We're starting again. Looks very much like our setup call. And then we simply draw the line. Any intuition? I see some light bulbs. Okay, I was hoping something would appear at the top soon. And now we have our little broken slate filled in with gold repair art generator here. Maybe I should have brought in some lo-fi music just to watch while this is going. All right. Let's play with this a little bit. Rearrange some windows. Get out of here. All right. So you can see the values that are being generated each time step. Oh, let me show off the stop and start function. I won't forget that again. In this case, S. Stop simulating. Do it again. Stop, start, stop, start. Okay, so I want to change just a couple things. So first, I want to set the starting X location to now be in the middle. There are 2 places I need to make that change there. And here. So every time we restart, we're starting in the middle now. So this will look a little funny for this particular use case, right? Because we're always starting in the middle instead of on the right. You'll see why we're doing this in a moment. And now what I'm going to do is change us from using noise to using random. Now it's undirected, right? It's just kind of swirling around. And if it moves meaningfully in one direction or another, it's because it got a lucky streak of random values. So this is just randomly exploring, randomly walking through this space. So before with the noise, we had our coordinate that we're at, and we want to move 4 in a direction. Well, when we're using noise, the change in the direction is smooth, like the gradient is smooth, right? You start moving like this and like this and like this, then you'll start moving like this back again and like this. It'll always be sort of like next to where it was in the previous direction. The new direction will be close to what it was before. With random, once again, instead of it being a more biased distribution around 0.5, we're getting a uniform distribution. It can be any value. So we're here, we'll move here this time. Okay, we're here. Now we can move here. Here? Okay, now let's move here. Okay, now we're here, move up again, right? So it's just randomly picking between the degree between 0 and 600 without any smoothness or any good gradient to follow, which is why you have this instead of the nice lines we had before. Okay. Any questions? We have 4 minutes left for questions. Comments, concerns? Did you learn something today? Excellent. Yes.
So, can you use processing for analyzing the data or research that you've done? Is this a
You can. I wouldn't recommend it. You'd be better off using MATLAB or R or something that's really made for visualization. But this is using Java, right? So Java's been used for data visualization lots of times. It's been used for anything from machine learning to graphics, right? So you can do it, but there's not a lot of infrastructure there to help you to do it. And if you want to talk about that more in depth, I'm happy to chat in office hours. Anyone else? Yes. Okay.
What's like, how am I gonna add comments, like notes? Like, what should we do, like, in the comments that in the program we wrote?
Yeah. So what I want you to do is explain to me what you're trying to do with the code near the comments, right? So if you have these 4 lines of code that animate your little crustacean mealyworm to roll around, right? And it's not quite obvious because you're just drawing a set of ellipses and then rotating them a bit. It can be hard to tell what that is. There's 6 lines of code. It can be hard to tell what that is. So if at the top you're I am drawing a mealybug. It is rolling. It is rolling because theta is changing. Right? That's the kind of thing we're looking for. We want to see the intent behind what you're trying to do with the few lines of code after your comment. Does that help? And I want to reinforce that we haven't really touched on this a lot, and this will become more important as the assignments go more extensive. You're allowed to include a text file with up to a page for 300 words explaining your assignment. So if you think there's something we may not interpret well, or you want to explain that, yes, I did understand this thing conceptually, but I couldn't quite get it to work here for these reasons, that's good information for us to have. Give us some explanations, show us what you're thinking. If we can have a better view of what's going on in your brain and you're communicating with us, partial credit's a lot easier to get. Particularly for something like these animations. For example, if you did a really detailed animation, you had this vision for a scene that was in 3 characters. And it would kind of ruin the scene if you had the 4th character, but you added a more animation detail to the first 3. You could explain that to us. Chances are you get full points. We'd relax that 4 moving object restriction, 4 animated things restriction, because you did something exceptional with 3. Any more questions? All right, it's 11:50. Have a great day. Good luck in your assignments. I'll be posting office hours when I find out exactly what time they'll be after I chat with the TAs. It's going to be hot out, so enjoy your 90-degree weather. Take care.